Welcome back to the New Quantum Era. I'm Sebastian Hassinger. My guest today is Izhar Medalsy, co-founder and CEO of Quantum Elements. Izhar is one of the more unusual founders I've encountered in this field. He's not a quantum physicist, but someone who arrived at quantum computing through a long arc of adjacent disciplines. He started in neuroscience, moved into physical chemistry, and did his PhD and postdoc work at the intersection of quantum dots and protein nanostructures, using atomic force microscopy to build nanoscale logic devices. From there, he spent more than a decade actually shipping complex hardware-software products, productizing AFM instruments at Bruker, then as chief product officer and CTO of Nexa 3D, getting one of the fastest resin 3D printers on the market to manufacturing scale. That combination of first principles physics and hard-won product discipline is a rare thing in deep tech, and it shapes how he thinks about the problem Quantum Elements was built to solve. The company, which he co-founded in 2023 with Harvard experimentalist Amir Yacoby and USC theorist Daniel Lidar, is focused on a layer of the quantum stack that doesn't get nearly enough attention: simulation. Not abstract noise models, but realistic, hardware-faithful digital twins of specific quantum devices, the kind of simulation that lets you understand what a machine is actually doing before you try to fix it. I should disclose that before I left AWS, I was involved in a collaboration with Quantum Elements that we'll discuss in the conversation, so I have a personal connection to some of what Izhar describes. The question underneath everything we talk about is a fundamental one. How do you build intuition about a quantum computer when the thing you're trying to understand is, by nature, mostly hidden from you? Izhar has a specific answer to that, and I think it's worth hearing. This episode is brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector. From drug discovery to material innovation to complex financial modeling, classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. Here's my conversation with Izhar Medalsy. Izhar, thank you very much for joining me. It's good to see you. Can you start by providing a little bit of context? You are not a physicist, so a little bit about where your training lies and how that brought you to where you are in quantum today.
Yeah, hi Sebastian. Great to be here. We've waited way too long to have this podcast together, so I'm excited. I'm excited to be able to do it. My journey started in really gravitating to where my interest lies. My bachelor's degrees was in neuroscience, and then I felt that I want to go maybe a bit deeper. So I've switched to physical chemistry and did my PhD in the intersection between quantum and nanoelectronics. So we were taking quantum dots, connecting them to very stable proteins that can create those two-dimensional lattices, and then using atomic force microscopy, I was actually able to realize nanoscale computational systems on rather than binary, on ternary state logics. So it was pretty interesting. And the idea is that back then was that, ternary logic is mathematically more efficient than binary. And so, yeah, it was, quantum dots, quantum charge effects, etc., but not quantum computing. Did my postdoc at ETH, and then once again said, okay, I feel like I need to reinvent myself again, and switch to industry, and took it from there.
And initially, I think you were in like 3D printing, I think was what you told me about your first sort of entrepreneurial venture was, right?
Yeah. The first entrepreneurial venture was 3D printing, but what led me towards that was my 15 years of experience with atomic force microscopy. So I
Right.
was developing atomic force microscopy technologies, kind of, hardcore scientific instrumentation. And I took my initial design as a scientist was then adopted by Bruker, and I kind of switched to, I call it the dark side of product management and biz dev, and took this product to the market. So it was quite a nice journey, kind of 2 years from really ideation all the way to launching a full integrated atomic force microscope that is connected to a confocal microscope. So it was quite a nice journey to really see firsthand how do you take an idea and kind of launch it into a product that's, has quite a high price tag. But what it taught me is this intersection between control, the mechanics of moving things, so control electronics, the mechanics, control software, and materials. So when I got the opportunity to build a 3D printing company, it kind of all came together. Obviously, I had to reinvent myself because I didn't know anything about 3D printers, only that they look cool and they make parts. But nevertheless, we made the fastest printing printer on the market. I was the chief product officer, then switched to the CTO, and it was quite a successful company, and for about 7 years. And yeah, that kind of led me to kind of rethink my view on another industry, which is the quantum industry. Kind of led me to where I am today.
That's really cool. I mean, it puts you in a very small group of people in the quantum computing community that has a scientific background, a PhD, postdoc experience, and entrepreneurial and operator experience as a chief product officer and bringing something actually all the way to maturity of the market. So that's a very, very rarefied set of skills, I would say, which is great. It's a huge advantage. So you've co-founded Quantum Elements with Amir Yacoby, who's a condensed matter physicist, and with Daniel Lidar, who's a theorist who we've had on the podcast, who's very, very well regarded in terms of, in particular, noise modeling and coherence and its effect on coherence.
Yeah.
Did the idea come out of the three of you all together, or was there sort of a sequencing of discussions with Amir and with Daniel that sort of brought you to the thesis that's represented by Quantum Elements?
So I'm going to say something that probably would resonate with a lot of people who build companies. And it is the fact that if you want to have a successful company, there's so many things that can go wrong. So choosing the people that you will go on this journey together with is probably the most important decision you're going to make. So I met Amir more than a decade ago. We actually worked on NV center detection systems for atomic force microscopes. And we stayed very close friends, and we felt that, together we can do something in the quantum space. And I'm also very good friends with Daniel. So the three of us kind of started the ideation process a few years back, where we looked at the industry, and I came with my background, Daniel with 3 decades of quantum scientific discovery, and Amir on the applicative side and as an experimentalist. And I also have a background in aviation, and for me, it was really amazing to see such a cutting edge technology, kind of like quantum, an industry that ultimately can really transform how society thinks about big problems and address them, really lacking fundamental simulation and development tools. So given the fact that we now have this amazing ability that Daniel really developed over the years to be able to describe quantum system from first principles in a very accurate way, not only how those qubits behave, but also how the environment affects them. and also solve those systems at a large scale kind of allowed us three to have this really very unique canvas to be able to say, okay, we think there is an opportunity here to build a company that addresses this key need to be able to understand how those systems are behaving at scale and provide the industry for, we think for every user persona in the stack, the ability to move faster with much deeper understanding of the governing principles behind the things that go well, but also go wrong.
Hmm. Interesting. So Daniel's work in understanding noise, I've heard you and him sort of refer to what quantum elements, sort of at the core of the value proposition for quantum elements is building digital twins of physical qubits. Is that right?
It is right. And the reason we're using this term of digital twin is because we are looking at the system as a whole. Where, when you have qubits, you have crosstalk. They influence each other. They don't work in isolation. When you work on a two-level system, you have leakage. Sometimes you will excite the third excited state. So you need to take all of those things into account, and you need to take them into account in the time domain, meaning how those effects evolve over time. Because, quantum circuits start at a certain point, and then through the gates evolve into the point where you measure your end result. If you're not able to see the evolution of everything that is going on in the system, you're effectively missing out on a lot of information that is critical to the understanding of what is going on in the system.
Interesting. So it sounds, it's funny when I talk to John Martinez, every time I've had this conversation with him, he will get around to essentially saying what he thinks his, strength is thinking in systems engineering terms, not just in experimental physics terms, but in understanding the broader dynamics of the system and how the dynamics can be marshaled and managed in a way to make a more predictable, more effective, entire system. Is that kind of how you see that? It sounds like you're saying, understanding those dynamics through the simulation of the digital twin can lead to better operations or better design of the system. Is that right?
It's absolutely is right, and I'll take it one step further. I think when you control a classical device, a 0 is a 0 and a 1 is a 1, the kind of physics is very well defined. You have a gate, you provide some bias, you're flipping the switch, you're opening or closing the tap. When you're looking at superconducting qubits versus neutral atoms versus ions versus, any other modality, each configuration, each modality, each QPU generation might have a different set of pulses and different strategies to just realize a gate. Once those gates are alive and they start interacting with other gates and and kind of idling or going through whatever processes that they're developing different noise processes and different noise errors that are all related to where they originated from and how they were realized. So, in other words, in order for us to be able to create the control stack for the quantum computer, we need to be able to understand where we're starting and where we're getting towards, meaning we have to be hardware aware. And the way to be hardware aware is to be able to look at the system from first principle, develop those digital twins, and scale them to a point that you can now address the main bottlenecks that the industry is facing, right? If you can save time and money on running hardware experimentation versus doing it on virtually, you'll get quicker to your end goal. Some of the, I don't want to be too cynical, but, sometimes when I look at the quantum industry and I kind of compare it maybe to the aviation industry, there are instances where you think, well, it's almost like building the next fighter jet or commercial airplane with wooden models in the air tunnel. You know, kind of shave it a bit. You put it in the air tunnel. You see if it shakes and and wiggles, and you kind of iterate again and again and again.
It's like
We
an
need to move
artisan
away
model.
from.
Yeah. Thankfully, we're not making quantum airplanes yet.
Not yet. Yeah. One day. So going back to where we are, I think those tools are critical, and using those tools, we can now be, as I said, hardware aware and accelerate the development of every layer in the stack, right? From optimized pulses for advanced gates and new gate strategies to reducing noise on the circuit level through error suppression and error mitigation that you can try and test on virtually and then implement on hardware, all the way to testing and developing new quantum error correction strategies and decoders.
Yeah. Okay. I want to sort of pick that apart because we've had this conversation before. And full disclosure, before I left AWS, I sort of helped drive the collaboration with Quantum Elements that resulted in a recent blog post, which we'll get into in a moment. But the reason I want to sort of probe the applications of your technology from that R&D phase through to like operational phase. So starting with design and research and development, you mentioned error correction. What we did together when I was with AWS, the collaboration with Quantum Elements, was creating a simulation of physical qubits that mimicked the implementation of surface code that Google had done with their physical chip. So talk me through how that was accomplished and what the value of that kind of simulation might be for a hardware vendor or other a commercial entity.
So we had to overcome a few scientific barriers in order to get to this result. But let me start with what is the value proposition? Why it matters? Why people should care? When you look at developing specifically surface code and then developing decoders based on that, the go-to platform is STIM. The advantage of STIM is that it's extremely quick. You can run relatively large systems using STIM. The thing is that it uses only Clifford gates, so it's kind of unaware of the noise that is the underlying governing principle of the
Well,
things that
and
limit your.
it is sort of the equivalent of like a classical circuit simulation, which has sort of assumptions. Maybe it doesn't assume perfect. It has a noise model, but the noise model is also very abstract, right? It's sort of
Exactly.
it's a toy model in a sense of what the real operating conditions would be.
Exactly. So
Yeah.
the goal we kind of set in front of us together with AWS and your amazing partnership was, hey, can we take our digital twins and enlarge them to a point where they can be able to address this kind of milestone of distance 7 surface code. Distance 7 meaning 97 noisy qubits. That's kind of the threshold where we can start looking at the conversion from physical to logical qubits using surface codes. Now it's very non-trivial, because if you look at the way that traditionally you're solving those master equations that are allowing you to take into account an open quantum system, a quantum system that interacts with the environment, they're very expensive computationally. So if you look at brute force, you're usually limited to about 16 qubits, because you just explode computation, and it makes sense.
It's sort
if we
of,
can
I mean,
brute
it's sort of proof that quantum computing, if it works,
Exactly.
will be more powerful than classical computing because it's impossible to simulate.
Exactly.
Yeah.
Absolutely. Otherwise, what are we doing here? We
Exactly.
can build a classical representation of any quantum device. So we had to come up with a new method of breaking those barriers. You have other technologies like tensor network, but they have problem with with the connectivity or the entanglement size of the system. So we had to come up with a new way of enlarging those digital twins to 97 and beyond, and we used a new method called that we kind of developed on top of quantum Monte Carlo using stochastic compression, meaning we are looking at the whole, let's call it universe of solutions, but really cherry picking the areas that there is sparsity in the system. And that allows us to maintain the noise models and this high fidelity understanding of what's going on in the system, crosstalk, leakage, and others, and take it to sizes that are big enough and to address this distance 7 and beyond. And in the blog post, what we've shown is that when we are running those kind of surface code, we are able to almost predict which qubits are more prone for developing errors, because we understand how their crosstalk affect the behavior of the system and other noise parameters that we really can insert into the system. And it's easy to see how once you understand the noise and the behavior of the system at such a large scale, your decoder should naturally be able to more faithfully predict the how to address errors as you're running codes.
Interesting. Yeah, I mean, it's intuitively it makes sense that if you want, I mean, it's so difficult to do what Google did, to stand up 100 plus physical qubits in an experiment and then operate them to get surface code implemented. There's so many plates spinning to make that happen, that if you can do that in a simulated environment, it feels like there's enormous opportunity to learn, as you said, where are the sensitivities, where are the things that really matter the most, versus things that you can sort of take more for granted. How can you how can you lay out the topology of the chip, or design the approach to fabrication, et cetera. Seems like there's so much you can learn that would make that, the next iteration of Google's Willow experiment easier to do, or someone else's implementation of their own surface code easier to do. So that makes total sense. And you mentioned decoding. I mean, decoding is sort of an invisible, unsolved problem in quantum computing. People talk about fault tolerance, they talk about surface or error codes, but decoding is where a potential error is detected and corrected. That's actually what makes it fault tolerant, and that's a classical loop in the middle of the quantum operation, meaning it's very, very sensitive to performance. Because if it's too slow, it doesn't matter how fast your quantum calculation is going. So do you see a role for quantum elements technology, not just in the design, but actually potentially in the operation of something like a readout scheme and syndrome detection scheme and feed forward, for that matter?
So it's interesting that you mentioned readout, because readout is one of the things that is still kind of not fully solved. We don't have robust models for readout, so that's something that is definitely of an interest for us. But I think another thing that we need to add on top of this ability to generate the digital twin is it creates really democratization. It allows teams in companies or independent companies to run a parallel track to the hardware development track. Meaning, if we go back to this analogy of the wooden models in the air tunnel, if you're able to develop decoders, predicting or hoping that the hardware will get to where it's supposed to get in time, you almost kind of accelerated the development because you don't sit idle and wait. the other aspect of having the ability to generate such a large digital twin that has all the intricacies and all the noise models that govern the behavior of a quantum computer is the ability to generate large amount of data and to train using this data different AI workloads, primitives, and models. And we might see, and we're not there yet, but we might see a future where AI decoders can work in real time in the quantum classical loop, because we're seeing a trend from the AI community to make more smaller models that can be deployed as an edge, meaning your edge compute resources are limited. They're not usually cloud connected. It's a computer that sits on an edge, whether it's a robot or whatever. In order to allow independence for those systems, you ideally would have a fully deployed AI system at the edge. It means that it has to be small enough and efficient enough to be able to work independently. So if we see the continuous drive of getting AI more effective, the continuous drive of making those GPUs more efficient, can we use AI-based decoders to ultimately be deployed on the quantum classical hybrid workloads?
Interesting. And would you classify? There's another experiment that you guys did. I think you announced it back in the fall at some point with the IBM Eagle chip, where you increased the logical fidelity from something like 45% to above 90%. I think it was 95 or 96%.
Yeah.
Is that the kind of sort of machine learning enhanced operation that you're sort of describing?
I think that's where it will ultimately develop towards. So what we've done is, you can address when you have the quantum circuit. Obviously, those qubits develop noise. One of the noise models that develop there are coherent noise, meaning those qubits kind of sit idle and they start to you can think of a spinning top where where the energy of the spinning top starts to go down, it starts to kind of wiggle. So that's kind of the analogy I develop and the intuition I develop for those kind of noise models. So you can address the physical qubit noise evolution using error suppression on the physical qubits. But what we've shown is that you can now go to the logical level and apply the same methodology and strategy on the logical level and address logical noise using those strategies, improving the overall circuit fidelity significantly. And that's kind of the next phase, right? The industry is talking about this transition from physical to logical qubits. We cannot assume that logical qubits will be noise-free. So how do you deal with the noise level on the logical system? And that's the work that we've shown with IBM that demonstrated this kind of additional capability. And if you think about how do you adapt that to every modality, every QPU, maybe every calibration cycle, you can do that if you're able to train AI models that will adapt to those changes in real time and will not require to run each time a full digital twin simulation. The advantage of running digital twin simulation is that you get the full density matrix, meaning you get the full picture of what's going on in your system. But in some cases, it can be computationally expensive. So if you add to the mix AI, now you see the very strong synergy between digital twins and AI to accelerate those kind of workloads and really build this full software stack that addresses the failure modes of the system.
Interesting. You mentioned all modalities. We've only been talking about superconducting qubits. Are you using the same technology on other modalities as well?
Yes. So we are now already showing neutral atoms digital twins. We have some very interesting results where we can run um, codes that using our capability on the digital twin, we can show significant improvement in performance. And we're definitely looking to add in the near future ion traps as well.
That's really interesting. And so we've talked about collaborative work that you and I did when I was still at AWS. So you've got an ongoing relationship with AWS. We've talked about your work with IBM. Now you're working with neutral atoms. And most recently, you've announced a partnership or continuation of work that you started in the past with Rigetti. Is there anything you can tell us about what the plans are with Rigetti? What that collaboration is meant to address?
Um, Rigetti, they've been amazing partners of us. We've been working with them for a couple years now. First, we showed that we can push the performance of their Novera system and the single and two qubit gate fidelity using our capabilities. Now, what we're doing is we're taking it deeper. I cannot disclose all the details, but what I can say is that using our deep understanding of how their system is behaving and through this ability to develop those digital twins of their specific system, we're helping them to pinpoint noise models and optimize performance through a closed loop operation, and really kind of be part of their roadmap to fault tolerant quantum computers.
That's really cool. And you mentioned sort of the ability to parallelize, with digital twin being able to run in multiple efforts. I imagine that's also really interesting from a pedagogical perspective, right? I mean, you can get a whole classroom running on the twins of the same physical qubit, so to speak. Is there a way for people to sort of kick the tires on the platform that you're building and try out the technology?
They absolutely can. They can go to our website, quantumelements.ai, get started. They'll get access to our platform. And what we are providing is something very unique. You can build your own virtual QPU. You can insert your own T1, T2 detuning. You can experiment with different connectivity. And once you're happy with your QPU, you can now run circuits and see the bit string output and experiment on different error suppression and error mitigation strategies, and then take it all the way to quantum error correction. Quantum computing runtime is expensive, and I think for a good reason. These are expensive systems that the companies spend a lot of money and time to build. But there should be a synergy between where you experiment and where you execute your workloads. You can try out a lot of things in the virtual environment, and then when you gain the certainty and the understanding of where you're heading, go ahead and spend with confidence on the quantum hardware. And I think it's a very nice way of getting faster to where you want to get with higher certainty and ultimately with better results.
Yeah, that was a leading question because full disclosure, I've already played around with your platform Constellation, as you know, and I think it's actually remarkably well designed from a UI UX perspective compared to a
Thank
lot
you.
of other products that are in the market. So it's quite a pleasure to use. And to your point, like lowering the barrier to entry, democratization, that D7 surface code experiment that you ran on AWS, that was on a large instance, an HPC instance, but I think the total cost was actually pretty reasonable if somebody ran that themselves, right?
Yeah, it's interesting. When we started, I'm sure you remember when we started this journey together, we thought that, it's going to be horrifically expensive. We were, I think, talking about thousands of virtual CPUs and terabyte of memory. You know what? We were able to optimize the code to ultimately run distance 7 on only 96 virtual CPUs and a few hundred gigabytes of memory. So yeah, it's extremely cost effective. It doesn't take too long to run such a large system. So we're very happy, and we're not stopping there. We're gonna keep on pushing scale and speed. To make it more accessible and to keep on pushing on this democratization aspect that you just mentioned.
Excellent. Well, thank you very much, Izhar. I think this has been really interesting. I'll put all the links in the show notes. I really encourage people to read the blog post, read your papers, and get on Constellation and try it out for themselves. So I think it's really exciting stuff that you guys are doing.
Thank you, Sebastian. It was a pleasure as always.
This episode is brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector. From drug discovery to material innovation to complex financial modeling, classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. My thanks to Izhar Medalsy for a really substantive conversation. The line that's going to stick with me is his analogy of building the next fighter jet with wooden models in a wind tunnel, a pretty sharp framing of where a lot of quantum hardware iteration still sits and why a serious simulation layer matters so much right now. You'll find links in the show notes to the AWS blog post on the Distance 7 surface code simulation, the IBM Eagle logical error suppression work, the Rigetti collaboration, and Constellation, where you can build your own virtual QPU and try this out yourself. If you want more from us between episodes, sign up for the newsletter at newquantumera.com, where we'll go deeper on the papers, results, and debates we cover on the show. If you're enjoying the New Quantum Era, please subscribe in the podcast app of your choice and share an episode with a colleague or a student who's trying to make sense of where this field is actually heading. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.